can talk in the beginning. But do you want me to ask if they have it?
Tell them to go on my channel, and I just started a new one.
Your channel? I'm about to go there right now. Georgia needs to go viral with all this.
I have to be
what?
what?
Send it in my group chats.
I have to be what?
You have to go viral so that you can get more subs.
What's your channel?
I want to.
Georgia Malou.
Eventually. I just started. I have one for Health in Harlem. I have one for myself. I don't know which one I'm gonna start for. I think I might do it for Health in Harlem.
I'll send your in my group chats. No, really.
I'm being serious. I'm just waiting a little bit. I reached a point where I feel like I'm so fluid with it that
Oh shit! What? That's touching you?
I want to get to the point where I'm so fluid with all of the systems that it feels like when I'm teaching, like right now, like I can just pull up any image and use it, or any resource, and I know what's happening. I just need something to help show what I already have in my mind.
You're like a robot.
I'm not.
No. Like if I
You know
had to
who's a
do all the
robot?
shit you had to do, I'd probably shoot my.
He's a robot.
No, not like that. Well, when I talked to him about some stuff, he seemed to know what he was talking about. Or maybe he was just making it.
Or
Who are you
just
talking
ask
about?
him, like, what color is blood? Oh, it's red.
Well, it depends if there's FE2 plus or FE3 plus. Guys are reduced. Bam. Right? No.
No, you're right. And which one's the reduced one?
So 2 plus is oxidized, bright red. Reduced is like metallic, but like like blackish gray.
Mhm.
That's yeah. No?
Yeah, you're right.
Okay.
I'm happy.
Me too.
Let's see, you remember that too.
I wrote it down like 50 times, so I remember it. And I remember I got it wrong on the AMP1 midterm, and I was so mad.
Can we?
Well, I'm happy you
I retained
that you knew you got it wrong, and now you remember it. There you go.
After
There you
the
go.
heart- After the heart, can we go with the infinity one?
Yeah.
No, I have so many questions.
Okay. So now, do we have people back? We have 7 people.
We had 11.
Okay. We had 11.
Yeah, 11 people were viewing last time.
Well, I emailed everyone.
Yeah. I got
Let me make sure nobody gets
it. And she's part of the 7.
Yeah.
Yeah.
This laptop is part of the 7.
Yeah.
Go. So it's a new live stream?
Yeah. So now it says part 2, and I've also emailed it. The only thing right now that I need to go back and kind of
After turbulence.
what I was talking about over here with the turbulence.
Well,
Okay. Well, do we have Victoria, Cynthia here?
Veronica too. Veronica's here. Maliha, Daniela.
Yeah, but I'm only saying those are the people who were asking me about that part. Or at least I think those are.
Veronica.
Okay. Okay, cool.
What?
Okay.
Kiara says,
We just hit 8. Guys, lab rules don't apply after midnight.
It's not midnight.
All right.
It's 11.
Yo, after 5, lab rules don't apply. After 5, basically.
Jojo, you're gonna get fined $3,000. You cannot be drinking.
Yo, look at y'all's teeth, yo. Damn.
I hope of a fire. Imagine a guy comes in right now. I'm doing fire inspections.
Okay, so Kiara's there. What?
Okay, we're up to 8 again.
Kiara's here. Daniela doing 9:30.
All right. I'm just gonna say what I was saying before. Okay, cool. So I'll go back to what I was saying before. Hey, Kiara. So I'm gonna go back to what I was saying before the stream got disconnected before, and then we'll continue. So there's what I was saying before was that you hear a lub dub sound whenever you're listening to the beat of a heart, and that's going to be, you don't hear things that are flowing laminarly, you only hear turbulent flow. So turbulent flow is like an ocean. So every time a wave crashes, you can hear that. And that's what's happening in your heart whenever you have your isovolumetric contraction and you have your ejection. And in both of those cases, you have valves that are closed. So you have a contraction, meaning that things want to move somewhere, but they have nowhere to go. So they just slam against the valve and they crash like a wave. And what that does is make a lub dub sound. So whenever you hear the lub sound, it's going to be the lub dub sound. It's going to be associated with either your blood hitting your mitral valve or your blood hitting your aortic valve, both of which are closed during this point. So you create turbulence, which is why you're able to hear that. But you actually have 4 different heart sounds, but the only ones you hear are those lub dub when you have the blood hitting against the valve. And over here, you can have an idea of what's happening.
Oh, man.
Oh my God.
Too sweet, bro.
Okay.
We're losing our minds.
Thank you for that comedic relief. Alrighty.
Okay, let's continue.
So what do we want to go to next?
I have a lot of questions.
So it seems like there was a lot of debate. Okay, wait. So is the lub dub hitting against mitral valve or dub hitting the aortic? Okay, so 1 second. Heart sounds, and you have 4 of them.
Yo, why is that shit on?
Oh, yeah. Are you tired?
I'm beyond tired. I could barely talk.
Need some water. Your palate.
I have an extra water bottle. Do you want?
Okay, thank you.
Need some distilled water.
Definitely don't need this still.
No, if you actually want to.
Some Jack Daniels.
Yeah?
I told you I should bro.
Stop!
Bro, man.
Drunk on July 28th.
Yeah. Yo. Did you know? Was it last class?
What?
Your last class, I was done.
Say that on the live stream, man.
What? He was joking, everybody. This is why I'm always dying over there. I have Malia to my left, Daniela to my right, and Mohammed in front of me. It's like disastrous.
What else do you want? Okay, finally got a good photo for you. So, yeah, let's use this one. Okay, one moment. Okay, so.
She says, okay, I got it.
That's it? Lub is mitral and tricuspid closing. Dub is aortic and pulmonary. Yeah. So you're going to have your atrioventricular valves shut while and making that lub sound, and then the dub is going to be when your semilunar valves are closed. So once again, you have 1, 2, 3, 4 different places where you have a sound, and that sound, as you can see, is caused by turbulent flow. Now, the thing is, the sound is much higher at certain points than others. So we hear lub dub because we're actually hearing your the point where your mitral valve is going to be slammed by the water, the blood that's in it against the closed valve. And then the other one is going to be the point where you have your aortic valve closed and your pulmonary. And this is the point where, again, that's going to be slammed with. All right. Okay, so what's next?
Oh, the P50 family.
Okay, let's do it. Try and fail, but don't try to fail.
Your curve is on next.
Oh,
I like that. Okay, so next up, we have our.
Oh, why does it hurt?
Man, this is such a relevant quote.
Try and fail, but don't fail to. Guys, we're getting really deep right now. Awesome sauce. Oh, tequila.
Did I hear that in a commercial? Awesome sauce. Oh my god. Who sits here?
You write on this?
You have to set your goal for the day. You have to live intention.
What?
Anytime I open a new tab, it asks me what's my goal for today. If I haven't set one, and then once I do, I check it off. Good job. And then it'll ask me, what do I want as my intention?
Mm-hmm.
And then it gives me a nice little quote. It tells me the weather and time and everything in different places in the world. It's awesome.
Very nice.
All right. So, oxy, hemoglobin dissociation curve.
What's my ass with this shit, bro? You don't hear that shit?
Okay.
Not meant for overweight brown people.
Oh, now you're overweight. I'm joking. I'm just kidding. I didn't complain.
Oh, you weren't complaining.
I need to lose 30 pounds. I need to lose 30 pounds.
Guys, we're live.
Sorry, I'm sorry. Okay.
Okay. Live. This oxyhemoglobin curve. So what you're seeing here is basically a curve that describes how saturated hemoglobin is, your y-axis, in terms of percent. So it could either be 0, 25, 50, 75, or 100, where it's 100% saturated with oxygen, because we have 4 different binding sites for each hemoglobin. Each hemoglobin has 4 heme units. Each heme unit has a single iron molecule, and that iron molecule will bind to a single oxygen molecule, meaning that you have in a single red blood cell, you have whatever number of hemoglobin. Each hemoglobin has 4 different places where oxygen can go, meaning that if you are 25% saturated, 1/4 of your 4 binding spots are filled. At point 2, you have 50% of it filled, where 2 of the 4 are now filled. At 75% saturation, 3/4 of your, on average, 3 of the 4 positions are filled. And then once you reach this point of 100, almost every single hemoglobin has 4 of their 4 spots filled. Okay, so this curve has a sigmoidal shape, which we know because of its S. That means that it's not under regular control, but actually it's allosteric regulation. So allosteric regulation has to do with modification of the shape of a protein in relation to binding that's not at the active site, but at the allosteric site. So this hemoglobin that wants to bind to oxygen from the iron and from the iron within its heme group, it's going to be more open to binding to other oxygens whenever one of its 4 sites are filled, because the other 3 will adjust their shape so that it makes it easier for the oxygen to bind. This is what we call cooperativity, because you have the multiple atoms cooperating with each other. So what that means is that once you get 1, it's easier to get 2. Once you get 2, it's easier to get 3, but then you get to slow down as you get close to saturation.
This is Dan Bilzerian thing, right?
Yes, meaning if you compare your library nerd who's never had any to your Dan Bilzerian Hugh Hefner who has many, Hugh Hefner would have a much easier time grabbing more playmates for his Playboy Mansion than library kid would have recruiting people to come to the library with him. So by the fact that you're already occupied, your oxygen is going to become that much more attractive. So that means that you're going to have a boost in the affinity between the first position being filled, which takes a lot longer to get, and then the second, and then the third. So this is an allosteric regulation. So if you watch the videos now again, I hope that this will help you to then realize Fe with nothing bound, everything is tight and accurate to actually bind to anything. Once one of them opens up, the other units will subsequently begin to open up, allowing for rapid binding of the next ones. So the conformation of your globular protein, the shape, is going to change to make it easier for the active site to actually be bound to. So it's going to make this, if this iron is full, it'll make this one more likely, and this one allosteric regulation. And that's going to be where you have, so instead of a regular enzyme was going to follow this kind of path, a logarithmic kind of change, where in the beginning it has a very quick change and then it slows down once it reaches a certain point, right? So with allosteric activation, you're going to, or cooperativity, you're going to have this S shape, so that in the beginning it's very hard to get anything, but then you have this huge jump between 25 and 75 where it's very quick to go from 1 position to 3. And the same is true when you're offloading. So you'll be able to offload just as quick because of this cooperativity. Because whenever you lose one, just like after a breakup, no one wants to talk to you anymore. On a tangent, animals, including humans, have a thing called mate copying. And females especially will do this, which is why I use that example. So whenever a female sees a higher level female on the hierarchy, right? Like your alpha female. If you see your alpha female going after someone, the person they're going after becomes significantly more attractive because you think if she's the alpha and she wants that, then she must be making the right decision. And therefore, I want it too, because that's what the alpha wants. And as a female, you need to be choosy because you have to pick the best possible mate to have. Then you have no reproductive costs. You can make millions of sperm a day. Females, you get all the eggs that you have for life in the beginning of your life by the time you're born. And then you shed one of them a month and hope that Prince Charming comes along, this one superior sperm. Right? So how do you pick the superior sperm? You look for the superior woman and you see, what is she picking? Maybe she knows better than me. Beyonce wants someone. You're going to want whoever Beyonce wants because you respect Beyonce.
I don't want Jay-Z.
All right. Maybe it doesn't work for Jay-Z, but generally speaking, that's the whole point there. All right. One last thing that I'll go over with hemoglobin. Oh, I'm sorry. So I spoke about what's the points, but we need to go back to what's actually happening here. So the reason why it's cooperativity is you get this sigmoidal shape. If there was no cooperativity in the beginning and then it slows down as it reaches saturation. Okay. So now hemoglobin has this curve and it's going to be dynamic. It's going to move left or right depending on the conditions, because why make a rule that can't be broken? It has to have exceptions, right? So here you're seeing hemoglobin, but we also see myoglobin. If you guys remember anything about the muscular system, you know that you have this red slow twitch muscle that's filled with myoglobin. And just like myoglobin, just like hemoglobin, myoglobin is a type of protein that has the ability to deliver oxygen, to onload and then offload oxygen. It's going to be found in the highest concentrations in your muscle tissue. So your muscle tissue has a lot of myoglobin. As you can see, myoglobin's curve is far to the left compared to hemoglobin, which means that the pressure, partial pressure of oxygen needed, or the concentration of oxygen that's needed to reach saturation for myoglobin is much less. So it takes less oxygen to fill up myoglobin, which means that it's P50, the point where it's 50% saturated, is going to be much less than hemoglobin's. So that means that this has a higher affinity, because with less oxygen, it was be able to pull all of the oxygen into the molecule. So easier to onload, harder to give up, because the affinity is higher. This is the person that I sent to get me a burger that wants the burger, is just as hungry. So it's not going to give it up, but it's going to go get it. So it's going to onload oxygen.
That's your vegetarian.
No. It's the myoglobin right now is someone with a high affinity for the oxygen.
Because it was low P50.
So it's going to grab the oxygen quickly. Great. Because muscles need oxygen for aerobic respiration to get all the ATP that it needs, the energy. The problem is, now it's so greedy with it that it doesn't want to give it away to the tissue, the muscle that needs it. Luckily for us, myoglobin isn't everywhere. It's in the muscle tissue. So it steals it very quickly and keeps it in the muscle where it's needed. Myoglobin will take oxygen a lot quicker
Very fast.
than
But
hemoglobin
it won't give it away.
because it has a higher affinity, a lower P50.
Yeah, I get that.
Okay, so because it needs very little to get saturated, it has a high affinity, a high desire for it.
So I'm not getting it away.
So you're not going to give away the things that you desire that much. But
Okay.
luckily, myoglobin isn't our main protein that carries oxygen. Hemoglobin is. Hemoglobin's a lot more balanced. It can pick it up and it could let go of it. And then it'll shift to the left or the right. So I'm showing you that myoglobin is a shift to the left, which means that it has a higher affinity. Myoglobin is high concentration in your muscles. Oxygen is going through your blood, and myoglobin goes, wait a second, and grabs it. Where does it grab it to? It's already in the muscle. You're good. That's where it needs to go. Do you get what I'm saying? Now,
No, I get. I'm just.
but now you're trying to see why would it offload.
Yeah.
Same thing with your hemoglobin. It's both going to be the same thing, where you have exercise is the right thing to do. A pull to the right is going to be associated with everything that happens when you exercise. When you exercise, you have an increase using the oxygen that you have at a quicker rate. You're hyperventilating.
Yeah.
You're beating harder. Your heart's beating harder.
Yeah.
You're beating harder. Your heart is beating harder, and you might be using more oxygen than you have. Using more oxygen than you have. Right? Like you're not. Right? Like you're not able to keep up with the needs. In that case, your carbon dioxide levels are starting to increase, and as you hyperventilate, your carbon dioxide levels also are going to increase because you're breathing so fast, you're panting, that just like your heart, if it was fibrillating or tachycardic, it's not actually moving anything. So your lungs, another type of pump, more like a piston, right, is going to be pulling in this oxygen so that now it could get into the hemoglobin. So in partial pressure of carbon dioxide building. So that's why you're seeing that whenever you exercise, you have a PCO2 increase. PCO2 is also a byproduct of metabolism. So as your cells are working harder to use the O2, to make your ATP, they're producing carbon dioxide. So that carbon dioxide is building up for two reasons. This 2,3-DPG is also another byproduct of metabolism. So that means that whenever you have an increase in your metabolism, because you're exercising, you also have an increase in this. Again, shift to the right. Now, the diagram I showed you also had H plus being increased, right? So everything on the right is increasing. H plus increasing is the same thing as pH decreasing. It's becoming more acidic, right? So a pH of 1, much more acidic than pH of 7. So as it drops, it means that your H plus levels are increasing. So for you guys who are trying to memorize all this, I would switch this to H plus and make the arrow an up arrow instead.
So, I'm just confused. Like you said, myoglobin is for muscle tissues.
Yeah.
And when it shifts to the left, myoglobin is taking up all the oxygen.
No. So they both will shift left and right. They're two different proteins.
Yeah.
Right? So hemoglobin is the main one. That's what I want you to know. But I'm just telling you, if you see a different one on that curve, you're able to use the same properties of the curve. Where is the P50? P50 is the point where 50% of your hemoglobin is saturated. So you look at where is it 50% saturated, and you slide over And then you go, okay, how much oxygen do I need to reach saturation? The bigger the number, that means that the affinity, they must not want it as much, right? Because I'm giving a lot of it, and it takes so much of what I'm giving for them to finally take it in. But if I only give them a little, and they take it all in, that means that their affinity must be very high. That's a shift to the left. So low P50, like myoglobin, means that you have a high affinity.
But when you work out, don't you need more oxygen in your blood? So
not in your blood, in your muscles.
Okay. That's why you have low affinity, so that they could give that shit away.
You have a high affinity, so they grab it.
No, the low affinity when you said exercise is the right thing to do.
Yeah. So when you're exercising, you want to get the oxygen to the tissue, not keep it in the hemoglobin.
Okay.
So you want it to go from being something that has a high affinity and can grab a lot of hemoglobin, a lot of oxygen into the hemoglobin, to the point where oxygen is able to offload or dissociate from the hemoglobin molecule. Hence the oxyhemoglobin dissociation curve.
Poof.
All right.
Wow, okay. So we did offload negative feedback loop.
Negative feedback loops. There's an audio being played.
If you're watching,
Matter of fact, yeah.
Yeah, if you don't mind.
It's not showing them.
Oh, wow.
The ovary.
Okay, well that's good.
The levels of during the
this is so weird.
menstrual cycle before ovulation. During the menstrual cycle before ovulation, small amounts of estrogen are secreted from the ovary. Estrogen stimulates the release of gonadotropin-releasing hormone from the hypothalamus and luteinizing hormone from the anterior pituitary. Gonadotropin-releasing hormone also stimulates release of luteinizing hormone from the anterior pituitary. Luteinizing hormone, in turn, causes release of additional estrogen from the ovary. The levels of gonadotropin-releasing hormone and luteinizing hormone increase in the blood due to this positive feedback effect. After ovulation, the corpus luteum is formed in the ovary and begins to secrete progesterone in response to luteinizing hormone. Progesterone inhibits the release of gonadotropin-releasing hormone from the hypothalamus and luteinizing hormone from the anterior pituitary. Blood levels of gonadotropin-releasing hormone and luteinizing hormone decrease because of this negative feedback effect.
One second. That one.
That's all.
I didn't. Yeah.
Really.
Yeah, I wasn't a big fan of that video. I had seen it before and I thought that I liked it, but yeah. Oops. Who should we give a chance to? Oh, Amoeba Sisters for sure. People are great.
Did you know just sitting here right now, you're doing something absolutely remarkable? Well, your cells, tissues, organs, organ systems, yes, we just leveled up those biological levels of organization, they're all working towards something called homeostasis. It's a state of balance. Yes, homeostasis means many things in your body. For example, that your blood stays within a certain pH level range. It means that your blood glucose remains within a certain range. It means your internal body temperature stays within a certain range. See, we've mentioned the major body systems before and that they work together. And today we're going to talk about how they work together using something called positive and negative feedback. and also how this relates to homeostasis. So many years ago, I had a pet bearded dragon. Her name was Debbie, and she was the best lizard ever. Debbie used to sit on our couch with me when I'd watch TV, and she loved to have her chin scratched. I even got her a bearded dragon leash so I could take her outside. Yeah, they make those. Anyway, Debbie loved her heat lamp. She would sit under the heat lamp on her rock, and when she got too hot, she would get off her rock and out of the heat lamp range and go somewhere else. She had a huge enclosure, too, because I wanted Debbie to be a happy lizard so she could find an ideal temperature. Why all this talk about Debbie? Well, Debbie is an example of an animal that some people refer to as cold-blooded, or a fancier term, ectotherm. We actually like the fancier term a bit better, though, because her blood isn't necessarily cold. Her body temperature can fluctuate with the environment. But not you. You are warm-blooded, or the fancier term, an endotherm. Your body works hard to keep the internal temperature it keeps. It's also a beautiful example of something called negative feedback. Before we define it, let us show you this example. Say you're in an environment that is very hot, like being outside in the Texas summer heat. That's typically hot. Thanks to nerves which can act as sensors, the brain notices this. It will send signals to counteract this variable. Sweat glands do what they do best, sweat. Heat is lost as that sweat evaporates off your skin. You may have some redness too. That's because your blood vessels are getting wider, dilating, in order to help get rid of that heat. And the result, whether you realize it or not, helps you lower your body temperature. But wait, what if you go inside now and the AC is blasting? You'll stop sweating. You may even shiver. The muscle contractions of shivering can generate heat. And those blood vessels will now decrease in diameter size, constrict, to help you conserve the heat because that makes it harder for the heat to escape. Your body temperature can increase then. This is negative feedback. So a simplified definition, negative feedback is when some variable triggers a counteracting response in order to come back to some set point. If we consider that this whole thing is actually a negative feedback loop, we can see that the negative feedback brings the body back to the set point, which in this case is a stable temperature, keeping homeostasis. Negative feedback is also going on in the regulation of your glucose, your blood sugar. Okay, we're really simplifying this here, as we often do. But when glucose, blood sugar, is too high, one hormone that is released is insulin. I always imagine insulin as this hormone that makes the cells say, feed me, because it has the ability to make cells take in glucose. On the flip side, if glucose is too low in the blood, a hormone called glucagon can be released. This hormone can have many effects, and one of them is that it can cause the liver to release glucose into the blood. There's more to the regulation of blood sugar than this, but you can see how this is negative feedback. You have counteracting responses here in order to keep homeostasis. So, what about positive feedback? Positive feedback is when, instead of getting a counteracting response to some variable, you instead intensify the variable. Positive feedback can be like more, instead of let's counteract this. The example that always stuck with me when I was a student is the example about the human baby being born. In biology classrooms everywhere, it's a classic example. When a human baby is ready to be born, there is pressure on the cervix, and that pressure and the hormones involved cause contractions of the uterus, because that's a big part about how the baby is going to be born. More release of hormones will equal more contractions and pressure, which will cause more release of hormones. More release of hormones will mean more contractions and pressure. Contractions help get the baby out, but it's also a part of a beautiful illustration of what positive feedback can do. So why do we care about feedback? Other than, the importance of negative feedback in maintaining homeostasis and the role of positive feedback in many body processes. Well, we also need to understand feedback so we can understand what is happening when there is a problem in the feedback systems. One example, perhaps you've heard of type 1 diabetes. It's a disorder that can mean that your pancreas, which is an organ that is involved with making some hormones like insulin, is not working correctly. Insulin is not produced, and because of that, one issue is that you're not going to be able to get glucose, the blood sugar, into your cells. Glucose outside of the cells cannot be used in cellular respiration. The cells need to take the glucose in to make ATP energy in cellular respiration. Therefore, your cells need to be able to take in the glucose to survive. So many type 1 diabetics need to give themselves insulin and monitor their blood sugar because the negative feedback may not work as it should. Well, that's it for the Meet the Sisters, and we remind you to stay curious.
So, controlling your blood glucose feedback loop. So, this is my favorite one to look at. Okay, so homeostasis, the point of where you want to be, the steady state. Your body wants to get to the point where you have, really this is pretty high. You would want it to be between 60 to 100. Right? So anywhere from 60 to 100 is considered normal. Anything below 60 is hypoglycemia, low blood sugar levels, or anything above that is hyperglycemia, high blood glucose levels. So let's say that I just ate a piece of Wonder Bread. Yes, Malia. So I just eat a Wonder Bread.
Kiara.
Oh, I'm sorry, Kiara. You guys had the same color, so I just was looking from afar. Apologize. So you have this homeostasis point, and then from there, you have the blood. If you eat this Wonder Bread, it kicks in. You start to the digestion process or catabolism, breaking down of the carbohydrates to its monomers. Once you get these monomers, which are these sugars, including glucose, your blood glucose levels increase. You get a huge spike. So your body senses, okay, I have a huge spike. So now from my pancreas, from my beta cells, I have to up my dose of insulin, and it's going to be endocrine signaling. It's going to go into the blood and travel.
Ductless, right?
Huh?
Ductless.
Through a ductless gland. It's going straight into the blood. So now that it's in in the blood, it's going to act on almost every cell. Almost every cell in your body has an insulin receptor that allows for the binding of insulin to it, which will lead to the uptake of glucose. So, sure. Okay.
For who's the really hate these?
You shouldn't. You shouldn't.
Shouldn't?
I know this.
Okay. So take a very good look at this diagram. We have two panels, A and B. Nothing happened in there, right? Okay, cool. So you have two panels, A and B.
Bye, thanks for the
No problem, Leah. It was my pleasure. All right. Yeah, I mean, she'll hear it tomorrow, she said. I think. Oh no, that was, I'm assuming what Kiara was
yeah.
insinuating. Alrighty. So pay close attention to this for whoever is left. In the first panel, you have insulin not bound to the insulin receptor. When this is happening, your secretory vesicle that's inside your cell that has your glucose transporting protein, GLUT4. So GLUT4 is right over here attached to this vesicle. And vesicles, for the most part, are going to be made of the same thing that your membrane is made of. It's almost like having a cell in a cell, right? So whenever your insulin binds to this, it's going to trigger a reaction through a signal transduction cascade. But before we get there, notice that the glucose over here is not being transported to the inside of the cell. It's staying in the blood. So if you have type 1 diabetes, you're not making insulin. You can never have insulin bind here, meaning you can never have glucose come into the cell. It will kill you.
That's innate.
That's your immuno. Yeah, it's a autoimmune disease.
Yes, that's what it's decided.
So you have your white blood cells attacking your beta cells and your isolates of Langarion that are in your pancreas. And because you have destruction of the beta cells, you never make insulin, which means you'll never have it secrete in the blood, or at least it's not at a level that's high enough to allow you. Right. So now let's look at the case where we do have insulin and everything is working normally. So if you have insulin, insulin binds to the receptor. That sends a signal through this cascade to the GLUT4 vesicle to then become exocytosed. Exo means out of, cell, cyto, and this is the process of. So the process of kicking out this vesicle from the cell starts. As it starts to get exocytosed, we have these GLUT4 that are here, and look at that. They're now on the membrane. Your protein moved from being inside the cell, not interacting on the membrane, to now becoming a part, integrated in the membrane temporarily, allowing for glucose to enter through this protein channel. Facilitated diffusion only happens when you have your insulin bind to this receptor, creating that cascade.
You got it? Yeah.
Yo, bro, if you didn't say that, I would have think that shit still stayed there, and then these came out of nowhere.
Which is why you need to look at everything that's changing. Like, that's what's happening there. So all of this is to allow for your GLUT4, your glucose transporter number 4 protein, because they found a couple of them that do it, but almost always it's going to be GLUT4 that we talk about. So GLUT4 is able to grab the glucose and bring it in through the channel. Channels on a membrane are made of protein. So that's your transport protein.
Poof.
So back to this diagram. When your pancreas releases insulin, it goes into the blood. And it tells your blood body cells to take up glucose, like we just saw. Which means it goes from the glucose is no longer in the blood, it's in the cells being used to make ATP through the whole process of aerobic respiration, right? So you're going to have glycolysis, you're going to have the whole metabolic pathway of aerobic respiration. We'll go through the Krebs cycle, all of that stuff to make the ATP, the electron transport chain. And then you end up with your ATP. So this means that you took the glucose from the blood into the cell, which decreases it back to its normal level. So at the same time, the other way that glucose is used is for glycogen storage. So we have a whole bunch of glucose, and we don't want them everywhere. We're going to make sure that we neatly package it into this unit. We're putting it into a glycogen, a polymer of glucose. So a monomer of glucose, a polymer of glucose, glycogen. So glycogen is stored rather in your liver.
So then what's this?
This whole thing together.
No, this is the liver.
No. You have many of these in your liver. Right? So this is in fact, this is just polymers of glucose.
That's the glycogen?
Yes.
Okay.
So glycogen is like 60 glucose together in this one box.
Mm-hmm.
So you transport this box to wherever you need to break down the glycogen to make glucose.
Okay.
Right?
Which is where?
Which you'll see in a second. So, so as this is happening where your pancreas releases insulin, it promotes two things: glucose uptake and glycogen creation and storage.
Wait, what?
So at the same time as you're putting, insulin is being secreted for one reason. The blood glucose levels are too damn high, and I need to make sure that we lower it.
Okay.
How are we going to lower it? We can either put it into the cells, or we can package it so it's not so damn messy.
Okay.
Because free glucose is what's toxic, but this glycogen that we store in our liver, not toxic.
Okay.
Your glycogen stores will last you 12 to 16 hours, which is why intermittent fasting is when you start to burn fat. Because you run out of glycogen, now your body switches to the next source, fat, for energy. After the fat is burned, it switches to protein. And it starts breaking your protein that make your muscles to use it for energy, which is why you end up looking... Your bodybuilders going through Ramadan, they end up losing muscle mass. Because intermittent fasting over time means you've used up your glycogen, you've used up your fat, now it's proteins. But before that, you have glycogen as the where you store your glucoses together. And if it's in glycogen, that means your blood glucose level is now lower, which means it's back to normal.
Ta-da.
So this signal, the fact that you went back to normal, tells your pancreas to stop releasing insulin. So the fact that the imbalance is corrected means that the loop is shut off. It gets feedback that you've reached completion. Stop doing what you're doing.
So is this going back to negative and positive feedback loop?
Yeah, so right now this is a negative feedback loop. So blood glucose level low triggers a reaction of insulin releasing. Insulin brings blood glucose level back to normal. Pancreas stops releasing more insulin.
Blood glucose level low means insulin gets released?
No, high means that it's being released to lower it back to normal.
Okay.
So you don't want low or high. You want normal.
Yeah.
Right? So you're going to make sure that you get to normal and don't keep going.
Going down.
So you need a way that you get feedback to shut it off. Am I good yet? Am I good yet? Okay, I'll stop. That's what's happening. So kind of like how I was asking you, do they have questions? I need feedback from you to know that I've covered this sufficiently, or are they
same like receptor?
We're doing that right now.
Oh shit. All right.
So now the other part of this is your, if you have too low of the blood glucose levels. So now you need to create more. So let's say you're intermittent fasting. Now your blood glucose levels are starting to lower. 10 hours later, you're like, wait a second, or even shorter than that, rather. So you just woke up and you're like, okay, I haven't eaten in a while, so that glucagon is going to start to come out because you went below 60, let's say. So you don't want to end up in an insulin shock. You want to be normal. So now your blood glucose is going to be raised through glucagon.
Yes.
How does it raise it? By telling it to release glucose back into the blood.
No, wait, look at this.
Making a mess of it, bro.
So,
oh my god.
Okay, so normal is 90 to 100.
Okay, BGL is too
low. It hits 60.
Yes. Glucagon release.
Glucagon is released from your alpha cells.
Mm-hmm.
It goes into the blood,
okay.
Gets to the liver, which is one of your filters of blood to remove toxin. It gets to the liver, and this also happens to be where we keep all of our glycogen. This is the warehouse So now it gets here. And glucagon is going to make the glycogen get broken down into glucose.
Wait, repeat that. Glucagon. Okay.
Takes the tissue box and makes it release glucose where? Into the blood. So if
PGL
glucose is being released into the blood glucose level or concentration is increasing to the point where it becomes normal. Once it gets normal, this whole correction mechanism is stopped. No more glucagon. And the cycle is stopped because you're at where you want to be.
Okay. So the tissues are what again? Tissues are glucose.
No,
Individual
glycogen.
tissues are your glucose.
Yes.
So this is one glucose. This is 2, 3,
Yeah.
4, 5. 60 to 100 of them we're going to put in this little box. And this is your glycogen, your
Yes.
polymer.
That's in the liver.
He's the liver.
A lot.
I have multiple ones of these.
I'm the
So a
glucagon.
lot of.
Yo, release that shit. Baby.
Release. So we break this box and we just allow the glucose to be
goes
released in a huge amount.
So tissue glucose. This is glucagon. Your liver.
No, that's glycogen.
Glycogen. I'm sorry. Glycogen.
I'm glucagon.
Yes. He tells me we need more of your tissues.
Yes.
So
I tell him I have a couple boxes of
so
that.
let's
I got you.
box.
So he tells, yes,
Okay,
so
okay.
I got you, fam. And then I rip open one of the boxes, glycogen. I can do that for so long because I only have a limited number of these boxes. That's when your fat reserves come in. When I run out of boxes, I say, I don't got you, fam.
Oh, okay.
That's when he has to now go to the adipocytes, your fat tissue, and say, we're going to have to burn our emergency reserves.
Oh, cool. Wow, that was a lot for one negative feedback loop.
That's a lot.
Okay, does anyone have questions? Because if you don't, goodbye. What's up with you in that?
Yo,
Wow, Georgia, that was good.
so how was it going?
Wait, what did you say?
I said I feel good. Yeah. All right, guys. Good night. Thank you so much for College of New York.
You sound like a radio person.
Oh wait, I am.